In this short lecture, I will describe how the iterator pattern can be used when implementing other things than merely a common interface for iterating over different backend stores. So, in the literature, you will find, or rather in the Gang of Four book, you'll find an example where the iterator is used to capture iteration and to provide a common interface for iterating different sets of objects. Iterating over lists, arrays, or hash table objects can be done in the same way by encapsulating iteration in the iterator object. So the iterator itself contains a reference to the current object that's referred to, and also the next object if there is one, and a way to calculate whether there are more elements. But we don't have to be restricted to such backend stores. If we say that the iterator is a common interface for iterations, and we can use it to iterate over anything, then we can create some things that are not even backed by data structures. In this case, we create a set of even numbers, an infinite sequence. We use a base class called enumerable, and this enumerable class contains implementations of methods such as where, take until, skip until, and so forth. But the important thing is here how we what we use as an iterator when iterating over sequences of even numbers. By the way, we use built-in API in Java where something that is iterable can be a target for the for each statement, for instance, but it also contains a method to obtain an iterator where you can iterate over the sequence with a returned iterator. In this case, we have an anonymous implementation so that every time we want an iterator for this even numbers class, we obtain a new iterator. So we iterate over numbers beginning with 0, and when we obtain the next value in the sequence, we add 2 to the current value and return the current value. And we always answer that there are more elements in the sequence of even numbers. Of course, this is limited by the upper bound on the int data type, but we could imagine that we have data types where integers can be of arbitrary size and not fixed size, as here. So, this is a perfectly legal implementation of the iterator interface in Java, where we say that there is no way to remove even numbers. There's always a next element in the sequence, and we obtain the next element by calculating it from the field num, which we use in our class. So there is no backend store, as in a list or an array or a hash table, but we calculate values. In this main example that we use a set of even numbers, and we manipulate that set of numbers so that we use methods to skip the first 3, take the first 10 of the remaining elements, filter those that are divisible by 4, selecting a string representation of the resulting set, and for each one printing it. Now, chaining methods like this assumes that whenever we apply a method such as skip or take, we return something that is of type, a common base type. So, in this example, whenever we apply a method the IEnumerable interface, we obtain a result which is also of type IEnumerable. So the only exception to the general rule here is if we apply the select operator, where we select based on a sequence of t elements, we obtain u elements instead. So we obtain an IEnumerable parameterized by u instead of t, whatever u is. In our example, we select a string representation, meaning that we map from integers to strings. So t in this case would be integer and u would be a string. So these methods, concretely, are implemented in the IEnumerable class, where we describe that when the common theme for all of these methods is that we obtain a new enumerable type object for each method, for select, where, and so on. And the core is that we obtain a new type of iterator, a new way of enumerating elements based on the definition of the current method. So a select iterator, for instance, would be one where we select the next element as long as there is an element from the source iterator to iterate over. So we create our select iterator by having a source iterator from which we can obtain values, and then we produce new ones by using something called a selector. So this select iterator has common functionality for every way in which we can select elements. So we only have to implement the single method in the iSelector class in order to provide a new mechanism for selecting elements. And that mechanism should return something of type u, given input of type t here. So we can look at our example where we produce a string representation from the method getStringRepresentation. In this getStringRepresentation method, we create a new selector which contains only one method, select, where we map from integers to strings simply by creating the string num : and then the string element, and then the integer element. So this string representation can be used when we invoke the select method. So the select method takes such a selector expression and creates a new iterator for us. So looking at the definition of enumerable, where we return a new object for enumeration that has its own definition of how to iterate over a sequence. Iterating over a sequence by creating a new select iterator. So the select method can be used for any enumerable sequence here to create a new sequence where elements are of type u if they initially were of type t. So the current class is parameterized with something called t. When we apply the select method, we obtain an IEnumerable of type u instead. And the same pattern can be seen in the where, take, until, and other methods that provide us with new iterators. Each type of iterator is specific in how we filter elements from a sequence, and this sequence, the original sequence, is defined by an iterator as well. So the where iterator here is one that filters elements from an original iterator. given an original iterator from a sequence of elements, we say that there are more elements as long as there are more elements in the original sequence. But we only select those elements where the predicate accepts the current item. Predicate being a parameter to this where iterator. So just as with the iSelector, which selects element, now predicate accepts element and can be used to accept or reject elements in a sequence. And if we go back to the main example, selecting elements divisible by 4 can be done by creating a new predicate that accepts elements where the remainder, when dividing by the base parameter, in this case 4, is 0. This means divisible by 4. So such a predicate can be used as a parameter to the where method to create a new iterator for us, as well as the string representation can be used in the select method to create a new select iterator for us. Skip, take, and for each work similarly in that skip accepts a number and provides an iterator that takes elements as long as, so let's see, the definition of the method skip and the class enumerable looks like this. We should create a new skip n iterator based on the number to skip, and this skip n iterator first, when it's created, iterates over the first set of elements without paying any notice to them, and then, as long as there are more elements in the original sequence, returns them using the source iterator. And conversely, if we want to take the first n elements, as long as there are more elements as defined by the parameter to this type of iterator, we return the next one. So we add another condition in the hasNext method, where we require that we should not have exceeded the number of items that we should be restricted to. So, what have we shown? Well, in this example, if we read out what it says in total, all even numbers apart from the first 3 and the subsequent 10 apart from the first 3 that are divisible by 4, so each second even number then, should be selected a string representation of, and a string representation is one that adds num : to the representation of each integer. And for each one we apply the print action having a prefix and, well, also a suffix supplied when printing elements. So if we print these elements, we see that even though our even numbers was an infinite sequence, we modify this sequence by applying operators skip and take, so that we obtain an iterator that only takes the first 10 elements apart from, so 10 of the first 13 apart from the first 3. and prints it like so. So if we were to remove this part where we take only 10 elements, then our application would run for quite a while. Now, as long as there's buffer space, so the buffer in this terminal is actually limited, so we can't see the first 1,414,499 elements. So, this is an example of how the Iterator design pattern can be used to emulate streams, infinite sequences, and where we can combine iterators to create something else than simply iteration over different types of backing stores.